Okay, so as I was saying, I like to refer to each individual entry here as a cell because it's a lot like cells in a spreadsheet. So when you're referring to a cell, you give the name of the variable, and then you would give the row and column number. So for example, if I was looking to get to this cell right here, I would say picture, and the row number is what? What's the row number? 2. Very good. So they go from 0, they're 0 based, and the column number? 3. So that cell would be referenced as picture 2, and then another bracket 3. When you're using a vector of vectors, you can refer to them in exactly the same way. So when you're referencing a cell, you use the same syntax, although you can also use the .@ syntax that we talked about. So you could also write here, if this was a vector of vectors, not only could you write it the way I did above, you could say picture .at 2 .at 3, and that would also work. That would be the so-called safer way of doing it. And if you're using a vector of vectors, this is the way you declare it. So you start by saying, I have a vector, and then that vector, the type, is a vector of ints. Okay? And a very important thing is that you need a space right here. I didn't do a very good job of putting a space in there, but you need a space, and the reason, can anyone think of why you might need a space between those two greater than brackets? Otherwise it looks too much like the cout operator, and the compiler gets confused. The compiler's not very smart. Okay, so it would confuse that with another operator. And kind of the way, now the book did kind of give you a visual on how you can think of that. So it's kind of like you have this vector, okay, and it goes down to here, up to, I'm just going to say n minus 1. And then each one kind of consists of its own vector of ints. Okay, so it's kind of, that's why they call it a vector of vectors, because you have a single vector to start, this one, and then each entry is itself a vector. Okay, so it still starts, this would still be column 0, 1, 2, 3, 4, and so on. So that's the image you should have. Now, just so you know, that's not really the way it's represented in memory, because memory is really just one long row like that. So actually in memory, the first vector would be here. That's all the entries associated with the first vector. And then the next vector would be here. So in actuality, they are side by side rather than laid out in a table. And that's just because memory, it's the way memory is. So actually, in the computer itself, they're laid out side by side. But you can think of them as being laid out as a table. So any questions about that? That's the basic thing, and you kind of read about it, you have some experience. So I figured rather than belaboring these points, what I wanted to do is go through some examples today using vector of vectors, and I also wanted to talk about some memory issues with vector of vectors. And also an important thing, actually I'll do that now before going further, going to show you one thing. So if I write a program call it vector.cpp. So I'm going to declare a vector int, and here's that space. See? Space. In fact, I'm not going to use a space. I want to show you what happens if I don't use a space. Okay, so I'll just call this table for the time being, and that's all my program is. The reason that's all my program is I want to show you what happens if you forget to put that space in there. So let's move that over. Let's get another window. And let's compile. Okay. And that was vector.cpp. What do you mean there's no such? You're right, I do. Thank you. So nice to have all these eyes on things. Okay. Especially early in the morning. Okay. So you can see not a very happy compiler. It's right there. It is got issues, implicit, instantiate, blah, 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 implicit instantiation of undefined template, blah, blah, blah. I'm just really confused. So if we just put a space here and recompile it, it's going to be very happy. Wasn't so happy. Oh, that's... why is it not happy now? I didn't include the vector. So now it's not happy because I forgot to include the vector class. Now it's happy. Okay. So a couple of things with vectors that you got to be careful about. So first of all, let's say I know in advance it's a 6 by 5 vector. So I have a 6 by 5 vector. I know that for a fact. Okay? So you might want to immediately make it a 6 by 5 vector. No problem for the rows. By saying table.resize 6, I give it 6 rows. Okay? Give it 6 rows. Not so easy to give it 5 columns. Okay? You might think, how do I do that? And you might think, what if I were to do this? You kind of look at that and think, is that going to work? No. What that does is it first gives it 6 rows, and then it looks like you're waffling, and it gives it 5 rows. Okay? So it's just chaining the calls. It's like you said, table.resize 6 followed by table.resize 5. So it just looks to the compiler like you're a big waffler. So that doesn't work. What you have to do, in fact, is go through each of the individual vectors or rows. So actually RI is bad right here. Let's actually give it a mnemonic name. So what I really need to say is for row equals 0, row less than, I could say 6, so we'll start with 6 for the moment. And now I can say table row.resize 5, and that's what's required. So I have to go through each row and individually resize each row to be 5. So now this is give each row 5 columns. Okay, so I have to do it individually for each row. Any questions about that? Okay, just one thing. This hard coding the 6 is a little bit of bad form. Yes, we know it's 6, but it's a lot better if I say table.size. And the reason it's a lot better to say table.size is if at some point I were to change this, okay, I don't have to remember that I also have to change it down here. So it's generally better not to hard code those constants everywhere. Okay, so we have our 6 by 5 right now. And now we need to read in values or somehow assign it things. So we'll start by reading in values. So we know, so we'll say for, again, row equals 0, row less than table dot size, row, let's make this a little bigger here. So now we're reading. And again, we have to now read in, for each row, we have to read in all the columns. Now, here's a trick. Oops. Looks a little odd, so let me explain what I'm doing. So, table row, row is our current row, right? So this is saying, give me the size or the number of columns in this row. If I know that this is a rectangular matrix where every row has the same number of columns, I could replace that with table 0.size, and you'll see that a lot in our code because that's assuming every row has the same size. Now I'll show you in a moment, it's not required that you have a rectangular table. That's one of the things you get with C++ and a vector of vectors. You don't necessarily have to have it as a rectangle, but if you know every row has the same number of columns, you can use that notation, and I will right now. And I need to remember to declare column. Okay, and then it's just a normal cin operation. So I can say table, row, and column. And that will read it in. Okay? Now, that only worked because I resized first. So in fact, I'm going to show you what happened if I had not resized it to the 6x5 dimensions. But right now, it works because I've resized it to a 6x5 table. Now, at the very end, I'm going to print out the table. Okay? So again, for row equals 0, row less than table dot size, row plus plus, and I don't want to repeat all this. What I'm doing is I'm yanking 3 lines using 3YY, so that allows me to just go in and modify this. I'm going to make it cout. Okay. Now, to avoid really bad habits, this is going to kill you. I want to put a space between each entry. I could do this. Okay, and then at the end of the column, I'll put an end line. And I'll see this in a lot of your code, and you're going to say, find out that your script doesn't match Dr. Planck's script. And you're going to say why? Because let's actually look at the result first to show you that this is going to work. So first of all, always a good idea. Let's compile it. Of course, I have some errors. And that's what happens when you copy code that's wrong. You get to fix it everywhere. Okay, now it works. Okay, let's compile it. Okay, and because I'm not in the mood to always enter the input every single time in case I have an error, I'm going to create some input. So let's see, on row 0, let's do, just for simplicity, 0, 0, 0, 0. We're a 6x5. I know this is boring, but hey. Do easy things first. Okay, there's my input. 5x6 row, yes. Maybe. Yep. So, thank you, Rachel. Boom, 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 boom. That's more Midwestern. Okay, it's a 6x5. Thanks for pointing that out. Okay. So 6x5, there's our input. Okay, I can't show everything. So I redirect it from input.txt now, and it works. It printed it out perfectly. And you run this against Dr. Planck's script, and Dr. Planck's script looks like it produces exactly the same output, and it says your output differs from his. Anyone have an idea why his output might differ from yours, even though when you visually inspect his output and your output, they look identical? Yes? Yes. This is pernicious. This puts an extra space at the end of your output. There's actually an extra space lurking out here, an extra blank space. Okay? That's bad. That's a dangling extra space that shouldn't be there. Okay? So you have to go to some extra issues to get rid of that space. And there's different ways to do it. One way is to simply start by printing out the first, doing a priming right. So just write the first element in the column. Okay, because that's the only one that in some sense doesn't have a space in front of it. Then starting at column 1, instead of putting the space after, we put the space before. Okay, so in this case, we put a space before every entry we print out, except the very first entry. Notice we printed the first entry outside the loop. It's like a priming right. P-R-I-M-I-N-G. It is, I'll call it, so I'll call it priming right. It primes the pump. Sorry, it again is Midwestern. So in the Midwest, we had pumps on farms, and no, I did not grow up on a farm, but you prime the pump by pumping it, and that gets water up from the well. Okay, so this is kind of like starting the pipeline, and so it's called a priming right. And it's actually, although it's a Midwestern term, it is a standard computer science term, priming. Okay, but it comes from priming the pump. So we do the first write, and then after that we can put a space before each of the remaining ones. And when we do that, it will have the same output, except that now there's no space out here, and Dr. Planck's code will work just fine. Okay? Now, there's another way to do it. That's a priming right. I like it. I think it's elegant. Another way to do it would be to declare a flag first up here. So I could declare bool flag, first, or first right, if I really want to have it mnemonic. So here I could say first right equals true. And then down here I could say if first right let's see, cout table row, actually I'll always do the right, so we'll do cout table row column. Then we determine whether we're going to write out a space or not after it using first right, actually a space before it. So if it's a first right, we're just going to say first right equals false because it's no longer a first right. Else, we're going to print a space. Okay, so that's the other way to do it, which is we check to see whether it's a first right. If it is, we simply set first right to false because it's no longer a first right thereafter. Otherwise, we print the space. I don't like that as much. I think it's less straightforward using the flag, but either way works. So whatever floats your boat is fine. Okay? But that's important that you don't mess that up. Now, Did you copy that? Because I just showed you some good code for doing VFlip in Lab 2. So in Lab 2, you have these PGM files that are pictures. PGM files tell you in advance the number of rows and number of columns. So you want to display your VFlip program is asking you to flip the rows. So if you have a picture, you, for example, VFlip, will flip rows 0 and n minus 1. Then it will flip rows 1 and n minus 2, and so on and so forth. And you really need a table in that case to represent your picture, because you have to hold all of the picture in memory in order to do this flipping. So you can use the code I just showed you with the, you can't hard code the 6 and the 5, but you'll have read the number of rows and number of columns, so you'll have those in variables. So you can use this code to read in your PGM file, and then by the time you get down to here, so I'll just further comment this, read the table. So once you're, whoops, but not that, undo. :undo is a nice command to get to know in VI. It undoes the last action. Okay, so up to this code right here, you have a nice thing for what you need to do with VFlip in Lab 2. You use it to store the pixels of your PGM file. Yes?
Can you scroll down to the bottom part again?
Yep. So this printing out you'll eventually get to too. So you'll have in VFlip, just a sec, VFlip, do, okay, flip the rows using your algorithm. And then at the end, you print out the table again. Okay? Remember, this is a little messier than the priming right, but either way works. Okay? We good on that? Since you're taking pictures of this, let me also show you the priming right, just so you don't necessarily write lots of, we good here? Let's go back to the priming right so you can take a picture of that too. Oh, by the way, just a sec, take another picture. That should be column equals 0 for that. So just a second. Retake a picture. Okay, that should have been column equals 0 because we're starting at the beginning. Don't want to give you. Got it? Okay. So the priming right looks like this. Cout table row. We're printing the 0th column. Now we are starting at column 1. We can get rid of all this yucky code. See, this is why I like the, it's just cleaner, right? A lot less stuff being, lot fewer moving parts in my opinion. Okay, so this is the other way. Okay, questions? Okay, so in that case, move on to another example. Oh, by the way, you may be tempted to use a 2D vector for other things like h-flip. You might say, hey, why can't I also use a 2D vector for h-flip? If you go and look at the lab, you will see that we tell you you're not allowed to do that. Oh, that's lab. Oh, wait a minute. Okay, it says you must use a vector for the h-flip and v-flip programs, and then in boldface, you may only use a single 1D vector for the h-flip program. And you're like, why can't I use a 2D vector for the h-flip program? Because it's wasteful. Okay, so this is the first lecture where we're going to start talking about don't do inefficient stuff. And in this case, you don't need a 2D vector in order to implement the h-flip program. You only need a 1D vector because in the h-flip program, this is Chrome, right? Excellent. So in the h-flip, you read in one line at a time and you're reversing that row. So all you have to do is read in the row, reverse the entries. So here's 0. Let's say this was 6. This might be 1. This is 5. So with h-flip, you're just reversing each row. So you can read in a row, reverse it, and print it out. And you never need that row again. Right? You never need it again. So you don't need to store that first row. Therefore, you can throw it out. You don't need a 2D vector to store the entire picture. Whereas with v-flip, once you've seen the first row, do you need to keep it? Yes, because eventually it's going to be flipped with the last row. So with v-flip, you can't throw out the first row after you've seen it. So you need a 2D vector. You're saying, okay, what's the problem with wasting space? Well, with the small picture files you have, maybe not a whole lot. But let's say it's one of these high-res pictures, maybe like 10,000 by 10,000. Now, that's a lot of bytes. Okay, that's 10 to the 5th times 10 to the 5th, which is 10 to the 10th, which I think is something like 100 million maybe? Or maybe even, well, 10 to the 10th is 10 billion. Yeah. So you had a 10,000 by 10,000 byte picture. I know it's not that high res, but that's 10 billion bytes if you try to represent it using a 2D vector. That's a whole lot of memory. You might not have that memory, or allocating that much memory takes time. It's not free to allocate memory. It takes time. So you don't want to unnecessarily allocate memory because it slows down your program. That's why you try to avoid allocating memory that's not required. So in h-flip, we don't let you allocate more than a single vector because you only need a single vector, and therefore the program will run more quickly. Questions about that? Yes?
I'm trying to think about the h-flip, and it seems like it's still the same number of elements. I mean, you still...
It's the same number of elements, but you're not allocating memory. You can keep that 1D vector. You're not going to throw it away each time. You'll just allocate that 1D vector once. If you were to use a 2D vector, you would have to allocate 10,000 of those 1D vectors rather than one 1D vector. It's a big difference, it turns out.
But if you did it, it would still ultimately end up being the same number of elements, correct?
Yes, it's the same. You process the same number of elements, but you're not doing as much work on those elements. It's okay. Yes, you're still processing 10 billion elements if it's 10,000 by 10,000, but instead of allocating 10,000 one-dimensional vectors, you'll only allocate one. That's a savings. Okay? Just like think about manufacturing. I mean, in a plant, if you're manufacturing one girder versus 10,000 girders, or 10,000 cars versus one car, clearly it's faster to manufacture one car than 10,000. Okay? So it's just some savings. So we just want you to get in the habit of not doing inefficient stuff. Okay? And that would be inefficient to store it as a vector. Not to mention the fact that if you don't have that much memory available, your program wouldn't run. Okay? The first way, with HFlip, I'm only processing 10,000 elements at a time in memory. So my memory can handle 10,000 at a time. It might not be able to handle 10 billion at a time. There may not be enough space for 10 billion. Okay? So that's the other issue involved. You can do it sequentially. It's like tourism. Knoxville might host 1 million visitors over the course of a year. We don't have enough hotel rooms to accommodate 1 million visitors, but if we spread those 1 million visitors over 52 weeks, we can accommodate them. Okay, so that's another way of thinking about it. Okay, other questions? Okay. So the second thing I wanted to talk about briefly is the fact that these vectors, these 2D vectors, don't have to be rectangular. Sometimes you don't want them to be rectangular because they would waste space. As an example, suppose that what I want to do is have a table that represents the miles between cities. Okay, now I have to use indices like 0, 1, 2, 3. But suppose these were things like Knoxville, which I can't, Atlanta, Asheville, Nashville, let's say Memphis. Okay, again, I have to use. So clearly the distance from Knoxville to Knoxville is 0. The distance from Knoxville to Atlanta, I think, is on the order of 200 miles. To Nashville, I think it's on the order of maybe 120. Whoops, that's Asheville. I think it's about 90 to Asheville. About 120 to Nashville, and I think about 360 to Memphis. Okay? Now, so that's Knoxville. Now I have Atlanta. Do I need to really show the distance from Atlanta to Knoxville right here? No, because I already know what it is. I know it's 200 because 0, 1. So I really don't need an entry here. Okay? I know the distance from Atlanta to Atlanta is 0. From Atlanta to Asheville, geez, probably about 150. To Nashville is probably, we'll say, also 150. And to Memphis, I don't know, 400. I'm taking guesses. Please don't Google map it and tell me I'm wrong. Okay, so Asheville is 2. Same thing. We already know what the distance is from Knoxville to Asheville. It's right here. So we don't need it here. We also know what the distance is from Atlanta to Asheville. It's right here. So what I'm trying to show you is that as we add things, here's Nashville at 3, there's going to be a whole lot of dashes. Here's Memphis. There's going to be a whole lot of dashes because we don't need to know what these distances. Asheville to Nashville is probably 240 and something like 450. And Nashville to Memphis is probably something like 240. Okay, so we don't need to know all the entries. Now, unfortunately, the way I've written it, I still need a rectangular matrix because I can't very well, I have to have these entries somehow right there. But what if I had done it slightly differently? Okay, what if instead I had done it so that we had, again, 0, 1, 2, 3, 4. And now I'm not going to put in the... Okay, so again, we still know 0 to 0 is 0, but now we know that 1 0 is 200. And we know that 2 0 is 90. And we know that, so I'm basically just copying the first row right here. Taking this first row, and I'm copying it into the first column. Okay, then I'm going to copy this row 2 into the second column. And I know I'm still getting used to this tablet, so you'll just have to bear with me. And then I copy the third row into the third column. Okay, and then 0 to 40. And the last one is just a 0. Okay, so in that case, I now have what is called a lower triangular table. And in fact, what I could do is represent this as a vector of vectors where the first vector has length 1. The second vector, so I'll just put this length 1. The second vector has length 2. The third vector has length 3. Okay? So I actually can do it in a way where I don't have to have every vector be the same length. And that is fine. Okay, so if I was writing the code for this, it would be slightly different. Okay, I'll try to move this over here so you can kind of see it. So if I was writing, and unfortunately it's going to be a little hard, but I'll keep moving. There we go. So now, instead of up here, with always resizing it to be 5, it would actually become row plus 1, because you can see over here the length of the first row was equal to the row number plus 1. Same thing for row 1. It was 1 plus 1 was 2. For row 2, its length was 3. So in fact, here's my code right here. That's initializing a triangular vector of vectors. Little bit different. And then when I was reading, I could no longer say that the table was rectangular, so I couldn't use any more table 0 size. I actually would have to say the row size, because each row size is different. The point is, you don't always have to have a rectangular 2D vector. Now, often you will. It's very rare that I need to use anything that's not rectangular, but I want to show you that it's possible. And again, I just want to emphasize that I use half the space in that case. So again, it's a little more efficient because I'm not using as much space. And we do care about efficiency both in terms of time and space. Okay. So questions about our one-dimensional or our triangular ones. Okay. A couple more things, and then I am going to let you work out a problem. So the next thing I just want to quickly say is that when you are writing the loops to go through a table, there's two ways to go through a table. So let's say I have a table and I want It turned out that I mismeasured something. Or let's say, actually, I have my picture, and I want to add a value of 10 to every element in my picture. Okay, so now I have a vector again. I'm not going to show you everything, but I want to roll through the vector, so I'll call it a picture. So I have a vector int picture. I want to roll through it and add 10 to every element. So I'm just going to have here some initialization code. So just assume that it's already initialized. And now I want to add 10 to each element of the 2D vector. Okay, so I'm going to call vector of vectors 2D vectors. It just sounds better. Okay, so there's two ways to do it. I could do it this way. Row less than picture. I'm going to assume again that it is a rectangular one. Row plus plus. Whoops. This, though, is picture.size. Then column equals 0. Column less than picture 0.size. Column plus plus. And I could say picture row column plus equals 10. Okay, so that adds 10 to every element of it. Now I can do it in a slightly different way. I could, instead of rolling through it by rows, I could roll through it by column first. So I could change each of these, and now it needs to be picture 0. So now I'm doing it by column rather than by row. Whoops. And that works just as well. So each of those sets of loops does the same thing. One is going through it. If you look at one of these tables, the first way is rolling through it one row at a time. So it goes through row 0, then it goes through row 1, then it goes through row 2. How is the second? Does anyone know how the second way is doing it? Yes, man in blue. You were nodding your head. You know how to do it? What it's doing? Yep. You're looking to the left now. Yep. Yep. Can you figure out how the second way is going? This way. This way. Okay. That's okay. Don't worry. This brings you back. Okay. So the first way is going through it one row at a time. It does all of row 0, then it does all of row 1. Okay. So the question is, what is the second way of doing it? Very good. So it's going through the columns like this. It first does everything in column 1, then it does everything in column 2, then it does everything in column 3. They both work. However, you should always do it the first way. You should always do it by going row first. Again, it's more efficient. You think, wait a minute, come on. Really? It's more efficient to do it row first than it is to do it column first? Let me tell you why. Let's go back to this picture of memory, where the way I told you how it's actually laid out in memory. So the first row is first, then the second row, then the third row, and so on. If we row through it row first, notice what's happening. We go through the first row, and when we need to go to the second row, where's the next element? Right there. It's right next to it. So we roll through row 2, and when we start row 3, the next element in row 3 is right next to it. Now let's say we did it column by column. First it does it here, then it jumps to here, then it jumps to here, then it jumps to here. It looks like a hummingbird. Week. back all the way back to here. Whoop, whoop. All this work, jumping all over the place. You may think, really, does that matter? Why, yes, it does matter. There's something called cache memory. Ever hear of that? Like when you buy a computer, you get like 3 gigabits of RAM and like 2 megabytes of level 1 cache and some megabytes of level 2 cache. Those cache memories are super fast, faster than what is called random access memory. It sits right next to the CPU. When you read something, it actually comes in on what's called a cache line. So when you read something like 0, an efficient processor can actually bring in much of this entire first row. And a smart processor can keep in the pipeline bringing in other stuff. And so once it's brought in this first row, if the next entry is 1, it's a cache hit. Okay? It doesn't have to bring in more memory, it's already there. Same thing, it's already brought in the second entry, so you're not getting any what are called cache misses. Now let's go to the column case. You bring in and you change this entry, but the next entry you need to change is over here. Pipeline processor didn't know that. It was bringing in entries here, it wasn't bringing in these entries. Since you need now to go to here, this is called a cache miss. And it has to go out to RAM and bring in that chunk of memory. Well, while it goes out and brings in that chunk of memory, guess what happens? We're spinning our wheels or twiddling our thumbs, not doing anything. So cache misses cost us time. Cache hits don't. When you do it in what is called row major order, because you're doing it row by row, you don't get cache misses. When you do it in what's called column major order, meaning you're doing it column by column, you get lots of cache misses. And that slows down your program. Okay? I'm not going to test you on that, but if I see you writing it in column major order, you will lose points. Okay? You should always write it in row major order for the reason I just outlined. Okay? And maybe one day a Google interviewer will ask you why you do things in row major order rather than column major order, and you can think back to what I tell you, and it has to do with cache memory and trying to avoid cache misses. Yes? Yes, row major order is the first one, where you're doing it row by row. Okay? Okay, so quick thing. It kind of looks ugly to say vector, vector. Kind of hard to read. So in Dr. Planck's code, let's get rid of that. You see a type def for today. Yeah, it's so ugly. Okay, so you see this thing called a type def. What a type def allows you to do is, in effect, define a new type. So you have integers, you have doubles. What this is saying is declare a new type called an integer vec. I would have preferred he call it int vec to make it very clear that it is a integer vector, but he called it ivec. So this is a new type, and it is comparable to a vector of int. So it's a new type called ivec. What it really is a vector of int. So a type def is a, let's go back to here for a second. So a type def is a type and then the new type. Now, let's see if I can move this somehow. Very good. Okay, so here the type is vector int. The new type is ivec. And now, instead of always having to say here vector vector int, instead I can just, and I'm going to have to, let's see, sorry, I'm going to have to clear for a second. Now I can just say, nope, how about close, there we go. I can just say IVEC here, vector of IVEC, rather than vector, vector, int. All the compiler does is go through and replace IVEC with vector of int. It's what's called a substitution. So before the compiler compiles your program, it runs what is called a preprocessor. So the preprocessor just does a substitution. It substitutes everywhere it sees IVEC, right down here, it replaces IVEC with vector of int. And notice now it was okay to have these angle braces with no space. See, there's no space between the C and the right angle bracket. The preprocessor is smart enough to know what's going on now. So Dr. Planck does this a lot in his code. Feel free to do it in your code or free not to. But you do need to know what a type def is. Okay, it's just defining a new type. It's a convenience. Okay, that's all that's happening. Questions about that? Okay. Last thing, making copies of things. Okay, so when you have vectors, let's say you have a again, vector, now I'm going to use IVEC. I'll call it picture. And we'll also have picture 1. You're allowed to do this. Picture 1 equals picture. Okay, you cannot do that with 2D arrays, but you can do it with vectors. This makes a copy, a complete copy of picture, and copies it to picture 1. Not a big deal if picture is small. Huge deal if picture is big, like say 100 megabytes. That will slow things down. Okay, so you need to be careful when you write innocuous looking assignment statements like that, and they happen to be 2D vectors or even 1D vectors, because they completely copy the vector. Easy to write, very inefficient potentially. Now there's definitely times where it's right to do that. When you write vflip, you need to save one of your rows when you are doing the swapping. There's no way around saving that row, so it's very convenient to be able to use this assignment statement. So used judiciously, it's fine to do assignment statements. Used injudiciously, it will kill the running time of your program. For example, something that may seem very innocuous is that you write a function called, we'll call it do edit pict. So edit picture. We'll make it a return a vector IVEC. I know I didn't do it. That's a vector, sorry. That's an IVEC. So we're returning a vector IVEC, and we're having it take a vector IVEC picked. This is horrible. Oops, not only that, I can't. And then at the end, I'll return picked. This is horrible. You don't want to be doing this. What happens is it copies the argument. So whatever the argument is, it creates a copy of it and assigns it to pick. And then when you return it, it again copies out this entire 2D vector and assigns it to the result variable. Lots of copying going on. Really bad. Especially because in any big photo editor program, you're doing this a lot. How can we avoid copying? Does anyone remember? Yes.
Pass by reference.
Pass by reference. Very good. So you always want to remember to pass your, come on, there we go. You always want to remember to pass vectors by reference to avoid this issue. I'm running out of space here. That's why I can't write out here. Darn it. Nope. Okay. PICT. Tablet's not letting. And then we would have made this over here. We would have made it a void. Yeah. Okay, so you would be instead simply editing the copy of the picture that was in the calling function. So be very careful when you're dealing with vectors that you pass them by reference, because it is very inefficient to copy them. It can really slow down your program. Okay? So read Dr. Planck's notes about copies of things, because you want to be careful when you're doing your copies. It's certainly okay to do copying like in VFlip, but you need to be careful about it. You need to be judicious about it. Okay, we're going to close today with having you do something. I want you to try to do your own little program, and by that get some practice. So I'm going to go to this just quickly read this problem statement for a skew symmetric matrix, and I'll have to explain it, but just read it. Okay, that sounds kind of complicated, but let me show you what's going on. So here's a matrix, very simple one, 3 by 3. Okay, and that's what their matrices are. They are square matrices. When you take the transpose, you simply take the first row and make it the first column. Whoops, I can't do that. But the first row here, in the transpose down here, it's simply the first column, 0, 2, minus 3. Same thing, column 2 right here is 2, 0, 99, second row down here. Down here, or column 3 becomes row 3 down here. So the transpose is simply taking the row in the first matrix and making it the corresponding column in the second matrix. And then we simply, to get minus m, we simply multiply each element of the matrix by minus 1. So if you look at this original matrix, okay, so right here, this one here, I've simply multiplied each member of the original matrix by -1. So this 2 became a -2. This -3 became a 3. And what it's saying is a skew-symmetric matrix is one in which this transpose is equal to the negative of the original matrix. You can see, therefore, that this is a skew-symmetric matrix because the transpose of the matrix is equal to -m. Okay, so this is just Topcoder choosing something cool. What it wants you to do is take a matrix and find the minimum number of changes required to convert it to a skew-symmetric matrix. My interest in this problem is that it forces you to create a 2D vector because it's giving you the input as a vector of strings, and I want you to quickly write a program that will take a vector of strings and from that create a vector, a 2D vector of integers. And you'll have to use string streams to do that. Basically, you'll have to iterate through the vector and use a string stream to convert each element to an integer and then add it to a 2D vector. So what I would like you to do is basically have something that is create 2D vector that takes a vector of strings, which I carefully, okay, and I want you to create a vector of ints, call it table. So the strings are coming in like 0, 3, 6, 4, 8. So each each entry in your vector is a vector of strings. So you'll need an iString stream to convert each string to an int. Okay, you have about 5 minutes. Get a start on it. And I'll go over the solution on Tuesday. But just take about 5 minutes now to start thinking about how you would do this. Okay, so you're taking a vector of strings and converting them to a 2D vector of ints. Actually, I'll help you out. I'll even give you the resize table to have the right number of rows. Use a string then for each row in M. Put the string into an iString stream. Push back or convert read string elements into an int, push back ints onto the row in the table. And you can work together, it's fine.